Now in this video we're going to be talking about how to work with Ksp and find concentrations from Ksp. Now hopefully by this point in the video series you're starting to pick up on the pattern, the same thing we use to solve all types of equilibrium problems. But if you're not, one more video, hopefully this will click for you. Now the thing with Ksp problems is they really only fall into two categories because of how complicated the algebra can get. One category is find Ksp based on concentration, the other is say find concentration based on Ksp. And you'll see when we do this that you can quickly get algebraic expressions that are very difficult to work with and you need a numerical solver to answer. So, first thing you need to be able to do, identify the ionic equation. So I've got two reactions up here, lithium phosphate and yttrium carbonate. So based off the formulas, you should be able to write what the net ion equation is, and all it is the solid breaking apart into the ions. So if we look at lithium phosphate, we have 3 lithium plus 1 ions, and 1 phosphate ion, PO4 minus 3 AQ. Now, if you're struggling with finding these charges, go back through my previous videos, look about how to find charges in oxidation states, and also just pull out a table of polyatomic ions. But this is the reaction we're looking at. This is what our KEQ is based on. Lithium phosphate dissociating back into 3 Li plus 1 and 1 PO4. Now, with all equilibrium problems, there are 3 components we need. The first is that Ksp, our equilibrium constant, equals Q, component 1. Component 2, we need our expression for Q. In this case, it's the concentration of lithium cubed times the concentration of phosphate. Third thing we need is our IC table. Now, our IC table, 2, 3, 4, is going to be very simple for all these problems. We have our parent salt, Li3PO4, our ion, Li plus 1, phosphate PO4 minus 3. Now the nice thing about these problems is that because we're always going to assume we have a solid with none of the ions in solution. If we added ions in solution, these problems get very complicated, and again you have to go to a numerical solver. So starting concentrations are 0. We don't care about the starting concentration of lithium phosphate because it's a solid and it doesn't appear in our expression for Q. Now I'm going to keep this column in here. Unless you're being asked to find molar solubility, you really don't need this column because none of these terms appear in our expression for Q. But the change for the salt is always minus x. Change for the lithium here is going to be 3x because of 3 in front of the lithium, and 1 phosphate for the phosphate, so this gives us 3x and x. Now we are given the concentration of lithium is 0.163 molar. We aren't given the concentration of solid, we don't need it because it doesn't appear in the expression for Q, and we're not given the concentration for phosphate. Now, we are asked in this problem to find Ksp. How do we do that? Well, we can actually get this other row here, because remember, the 2 E rows are equal. So we get 3x equals 0.163, the concentration of phosphate at equilibrium equals x. So we multiply through, we'll get that x here is 0.0543. So that's our value for x, 0.543. So when you're asked to find Ksp and you're only given 1 concentration, this is where you're going to use the equality of the 2 E rows. 1 concentration should give you the extent of reaction. That extent of reaction can be used to find the other concentration. Now, if you're asked to find molar solubility, that's just the extent of reaction. So in this case, our molar solubility is 0.0543 moles of lithium phosphate per liter of solution. Regardless, we're being asked to find Ksp, so we're going to use this E row. And when we plug it in, and I've got my handy dandy solution set here, we get the Ksp of lithium phosphate equals 2.37 times 10 to the negative 4. Now, a common mistake with this type of problem, this is lithium concentration cubed, so you're going to need to cube this 0.163 and then multiply it by the 0.0543. And that will give you the Ksp. What if you're given Ksp and asked to find concentrations? Same approach. We have Ksp, we know that Ksp equals Q, and we know our expression for Q for yttrium carbonate. If we write out the net ion equation, it's 2y plus 3 AQ plus 3 CO3 minus 2 AQ. So this is going to be the concentration of yttrium plus 3 squared times the concentration of carbonate cubed. Now, I got my KEQ equals Q, I got my expression for Q. Now I need to build my IC table. solve, Y2CO3 taken 3 times, yttrium plus 3, carbonate. Because we're not being asked to find the concentration of molar solubility, we're just going to ignore this column for now. Yttrium and carbonate are both going to start at 0. Change in yttrium is 2x, change in carbonate is 3x. So we get the in concentrations are 2x, 3x, and we're being asked to find this square, the concentration of yttrium. So since we are being asked to find concentrations, we're going to need to put in the algebraic row. And what we'll get is the concentration of yttrium plus 3 is 2x squared times the concentration of carbonate, 3x cubed. The challenge with these types of problems, you've got polynomials here. So 2x squared is 4x squared, 3x cubed is 27x cubed. You will get 108 x to the 5th equals KSP. You're going to need to solve for x. Now, if you're not familiar with how to do this, divide the KSP by 108. That'll isolate x to the 5th. To undo a power, you raise a number to 1 over that power. So 4.98 divided times 10 to the negative 7 divided by 108 raised to the 1/5 power. And this will give you the extended reaction x. Once you get your value for x, you're going to double it to get the concentration of yttrium, and you're going to triple it to get the concentration of carbonate. So these are the two flavors of KSP problems. But again, the setup is exactly the same. KQ equals Q, get your expression for Q and build your IC table. Figure out what you need to solve the problem and what you're being asked to find. Go from there.